A matrix is a two-dimensional array of data. It consists of rows along its horizontal axis and columns along its vertical axis. When matrices store their data in consecutive memory locations that correspond to their row elements, they are called row major. When they store their data in consecutive memory locations that correspond to their column elements, they are called column major. OpenGL uses column major format for more efficient memory access. I define my matrix elements in row major form because that aligns better with my conceptual model. I convert them to column major form before submission to instanced OpenGL draw calls. Matrix multiplication is defined by the dot product between the row elements of a matrix with the column element of a second matrix. The number of row elements must be equal to the number of column elements. Matrix multiplication is not commutative, so matrix A multiplied by matrix B may not yield the same result as matrix B multiplied by matrix A. The reason why matrix multiplication uses row multiplied by column rather than row multiplied by row is because it leads to the correct size result. For example, a 4-row by 4-column scaling matrix multiplying a 4-row by 1-column vector would result in 4-row by 1-column result, which is what you want. If instead you multiplied the rows together, you would get a 4 by 4 result, which would be equivalent to transforming the scaling matrix in respect to the vector, which is not what you want. The main diagonal of a matrix has significance because it represents a correspondence between the rows and columns. The identity matrix has ones placed along its main diagonal. When you multiply a matrix by the identity matrix, the result is the original matrix. The identity matrix is analogous to the number 1 in multiplicative arithmetic. The transpose of a matrix is when we turn the row elements of a matrix into its column elements. For example, a 2-row by 4-column matrix would become a 4-row by 2-column matrix with the data that was in the rows now in the columns. In computer graphics, we have 5 main transformation matrices. Translation, which offsets a model's position, scale, which changes the size of a model, and the 3 rotation matrices for the x, y, and z axes that alter the orientation of a model. We use 4x4 matrices because they're large enough to perform all the transformations we desire. The transformation matrices are multiplied in the following sequence. First, the rotation matrices are multiplied with each other. It doesn't matter the order because it is a special case of matrix multiplication being commutative. Then the scale matrix is multiplied by the product of the rotation matrices. Then the resultant matrix is multiplied by the translation matrix. The rotation matrices and the scale matrix use overlapping elements. This is because the scale matrix affects the final values of the rotation matrix. The translation matrix places the transform values for the x, y, and z axes along the final column where they do not overlap with the scale or rotation matrices elements. This is because translation offsets a model by the same amount independent of its size and orientation. When we look at the rotation matrices, we see that each of them has a 1 placed at the main diagonal element that represents rotation around that axis. So, x rotation has a 1 placed at the element 0, 0, y at 1, 1, and z at 2, 2. This is because rotation around an axis does not change the position of a model along that axis, but rather the positions along the axes that are orthogonal to it. In the example of x rotation, this would be the y and z axes. The axis rotation function rotates a model around an arbitrarily oriented axis. The set2 orthographic functions creates a projection matrix where all the clipping planes are orthogonal to the viewing plane. In other words, it creates a viewing frustum that has a rectangular shape. The orthographic projection matrix has the following form. The left, right, top, bottom, near and far values define the clipping planes that form this frustum. The values along the main diagonal scale the model so that it is transformed from world space size into the frustum clipping space proportions. The values in the final column then position the model relative to this clipping frustum. If the model lies completely outside the clip space, it is discarded from rendering. The set-to-perspective function creates a projection matrix where the top, bottom, and left-right clipping planes are progressively separated by degree. In other words, it creates a pyramid-shaped frustum. The perspective projection matrix has the following form. Once again, the scaling values are placed along the main diagonal of the matrix. The single non-zero element in its final column is used to multiply the W component of the vertex, so that models appear smaller the further they are from the near plane. The set-to-view function creates a matrix from the camera's viewing perspective. It takes a position and target to calculate the view direction and an up vector to set the orientation. It has the following form. Here is an example of the view and projection matrices being set and then combined with the multiplication function to form the view projection matrix. The view projection matrix is then passed through to the vertex shader with the model matrix to process each vertex of the model. We perform these calculations on the GPU rather than on the CPU because it allows many vertices to be processed simultaneously.